Welcome to today's webinar titled Fault-Free Integrity of Urban Driverless Vehicle Navigation with Multi-Sensor Integration, a case study in downtown Chicago, based on a paper published in the spring 2024 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is presented by Kana Nagai. Kana Nagai is currently a PhD candidate in the Mechanical and Aerospace Engineering Department at the Illinois Institute of Technology. She received her BS and MS degrees in Mechanical Engineering from the Illinois Institute of Technology and a Bachelor of Architectural and Structural Design from Hokkaido University, Japan. Her research interests include the navigation integrity of self-driving cars in urban environments and sensor fusion incorporating technologies such as INS, GNSS, and LiDAR. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. Following the presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We will turn the time over to Kana.
Okay, thank you for the introduction, Beth. I'm Kana Nagai. Today, I'm going to present fault-free integrity of urban driverless vehicle navigation with multi-sensor integration, a case study in downtown Chicago. Yeah. Especially the recent years, the demand of self-driving car is increased, but at the same time, people might wonder if it is safe or dangerous or a kind of fear of the technology. So I'm interested in the safety of self-driving car, especially I am interested in developing the evaluation methodology. So the driverless vehicle must operate with a safety integrity level, but it is too hard at the urban environments. The reason because high, tall building block or reflect the signals, and it degrades the GNSS navigation accuracy. For a long history, our navigation field try to or suggest the integration of INS, and INS and GNSS has a good relationship, helps each other. However, the GNSS, sometimes in deep urban canyon, it cannot help INS correctly. So whether the navigation system can perform satisfactory integrity for driverless vehicle through the city is undetermined yet. So here I would like to present how to achieve navigation safety using GNSS, INS, and LiDAR ranging from local landmarks in real urban environments under fault-free conditions. First, I would like to say my integrity requirement. I said that we assume the fault-free scenario. It means the sensor is always working correctly. Only position error is a matter of the evaluations. For long history, our navigation field, especially in aviation field, try to quantify the integrity. And we use the two parameters. First is alert limit. Second is protection level. The error has to be bounded by the protection level, and the protection level must not exceed the alert limit. For example, in our integrity assumptions, I use the citation work and two big papers. But for example, we use the EU SPA integrity assumptions. Alert limit is defined 0.5 meter. And the probability of exceedance is 10 to the minus 7. That will correspond 5 sigmas. So that this 5 sigma is equal to 0.5 meters. From this one sigma, it is a standard deviation, becomes 0.1 meter. We call it the maximum allowable position error standard deviations. And our integrity requirement will set the range of the value between 0.05 and 0.1 meters. The reason because I use a range, because the integrity requirement cannot specify only one value. It is defined by the width of the vehicle, width of the street, or the vehicle goes straight line or turn left, turn right. Every situation, the fault-free integrity requirement are changed. So in order to correspond the variety of integrity requirement, in our presentation or in our paper, we consider the concept of range. Here is a more detailed of probability of exceedance and alert limit, but overall, we consider the maximum both side and ahead direction is 0.05 and 0.1 meters. Then we will define the continuity and availability requirement. That's really challenging because no one discussed about the continuity and availability of requirement for self-driving car. So this is a kind of temporary concept using only this paper, but the continuity, we describe it the travel distance in meters. It is defined by the maximum allowable, the position error of the vehicle for the entire trip should be smaller than the maximum allowable position error standard deviations. And the travel distance means the continuity of the travel when it gives us, when it meets this integrity requirement. So for example, this is the result of my simulation. I will explain it more details in a later. But there is a starting point, that's the evaluation ending point. However, the error exceeds more than the 0.05 or 0.1 meter. We define the travel distance the same as equal continuity is from 0 to, in this case, 3 kilometers. The availability, I follow the rule of aviations. It expressed by the percentage of total time meeting the requirement over 24 hours. We define the integrity requirement, we define the availability requirement for self-driving car is 24 hours. The 24 hours, it means 100%. The reason because the self-driving car will be used the 24 hours, 7 days. It means always. In the next step, we will extract the data of the environment. In order to that, we use a 3D map. This is our simulation site. It is a state street in Chicago, 9 kilometers in total. Every 10 meters, we set the waypoint. We use GNSS RTK for constellations, GPS, Galileo, GLONASS, and Beidou. At the starting point, initialization and alignment has already done. The environment is really unique because it consists of low-rise near open sky environment at the beginning. But if the car goes from the starting point to the north side ahead, there are downtown Chicago loop. It consists of more than 100 meters of tall buildings. So after we taking the building information from the 3D map, we project it on the hemispherical sky view. Then we overlap the satellite information on it. Here is an example. If the satellite information is in the contour of the building, we consider it blocked satellites. If it's not, it is a line of sight, so that we use only the line of the sight satellite information. However, in urban environments, also we need to consider the multipass effect. So we detect the reflection signals using the householder transformation. And after we exclude all blocked and reflected signals, or the satellites which participate in the reflected signals, we count the number of visibility. This is the GNSS evaluations, and the upper graph shows the GNSS signal visibility evaluation using the edge stop method. Our integrity requirement is edge stop is smaller than 5. And here's the result. The gray zone says that enough satellite, it means that edge stop is less than 5, and the black one is not. This blue graph or blue diagram shows a side view of the building height along the street. You can see from 0 to 2 kilometers, it is an open sky environment, which defined no disturbance. It means a black lines appears on here. After the open sky, intermittent GNSS availability area appears. It means the black and gray appears in turn. Sometimes we call it the GNS challenging environments. After the environments, a succession of GNS denied area continues. Using the same environment, we evaluate GNSS. I do not use INS or other sensors at all. GNSS navigation variability evaluation, and the integrity requirement is less than 0.1 meters. As a result, at the open sky environment, we can guarantee 100% availability. However, after that, the denied area continues. It means we can ensure, or GNSS can ensure the self-driving car safety between 0 to 2 kilometers, but otherwise it's not. The reason because once the car hit the overbridge at here, all of the cycle ambiguity is reset, and the RTK never acquires a cycle ambiguity resolution again. This result gives us clearly we need the multi-sensor integration navigation system. This is our multi-sensor integration architecture. We use the extended Kalman filter tightly coupled. We set INS for the prediction, zero velocity update, radar, GNSS, wheel speed sensor, non-holomic, and holomic constraint for the observations. We're doing the measurement update step by step, and after that, we do the time update calculate p-bar. I use this p-bar for the integrity evaluations. Also, we call the radar is an optional sensor because it's a relatively new sensor. And except the radar, we call it conventional sensors. Here's the details of measurement models, but I would like to notify that model 1, model 4, both measure the velocity in body frame. And when the wheel speed sensors measuring the velocity is close to the 0, the system automatically uses zero velocity update. If the velocity is not the 0, we use a wheel speed sensor, non-holomic, and holomic constraint. This is an overview of the sensor noise parameters I use in our integrated multi-sensor systems. There are lots of noise parameters exist, but I would like to show we use 2 types of INS. One is STM300 tactical grade. The other one is ELPS2 industrial grade. In general, the INS quality decided by the grade. However, it is not defined by some guidelines, more like decided by the sense of navigation field. The reason because INS complicated number of noise parameters. Here is an example. As you know that INS, we use 2 sensors, accelerometer and gyro, and each sensor consists of velocity random walk, bias stability, bias time constant, and bias repeatability. And combining 4 sensors together, we calculate the INS quality. But I'm interested here, what kind of noise parameter is the most critical for urban navigation? So I focus in the application of self-driving car in urban navigation. I would like to know the noise parameter, the characteristic. Especially we're interested in the gyro bias stability effect. The reason because the tactical grade and industrial grade, it changes a 40 times difference, as a noise parameter does not change so much. So in order to know which noise parameter is the most critical for our specific application, I compute the analytical INS position error models. I computed the two models, but basically both two express the same one. First we call it precise, the other one we call it approximate. The precise version we consider bias as a first order gas Markov, and approximate we consider it as approximate to the white Gaussian noise. The equation looks so complicated, so please check it if you are interested in the paper. But in both equations, it consists of 4 noise parameters. The INS drifting error is consists of acceleration, random walk, and the time, and bias, acceleration, bias stability, and gyro random walk, and this G is the constant value of gravity, and the last one is gyro bias stability. In order to verify these two equations is correct, I compare the drifting error to the EKF result. Here is a result, and x-axis shows the time for 60 minutes, and y-axis shows position error drifting. You can see that EKF blue lines are precise, almost follow the same trajectory, and approximate a little bit off at the 60 minutes. However, if we change the time window from 60 minutes to the 20 seconds, these three lines follow almost the same. Only the precise has jitters. The reason because this minus term appeared. Back to our integrity requirements. We're interested in the 0.1 meters maximum allowable position error standard deviation. It means we're interested in the only several seconds, in this case, 15 minutes drifting error is important. And so that in this specific application, we can use the both precise and approximate error drift equations. In this presentation and the paper, I consistently use the approximation error drifting equation because it is simple. So now we're interested in how much each noise participates in the total drifting error. And in order to know that, I plot these values separately. Here is the result. The above one shows the STM300s, the below one shows the ELPS2, the tactical grade and industrial grade. And x-axis shows the time, y-axis shows the error, drifting error. And if the time window is 20 seconds, gyro random walk and accelerometer random walk, this yellow and blue line, is the top two in total error. And the gyro bias stability described by this green line is not important for a shorter time period. However, if we change the time period from 0 to 60 minutes evaluation, it's interesting the gyro bias stability becomes the top, and it is the most important INS noise for, it becomes the most important INS noise. But again, our specific application for self-driving car in urban navigation, only the 15 minutes is important, so that even though we use the STM300 ELPS2, it does not change so much. So finally, I showed how much drifting error reaches our integrity requirement, 0.1 meters. it says that both STM300 LPS2 goes to 15.5 seconds. It shows only under the self-driving requirements, this STM300 tactical grade and LPS2 industrial grade INS gives us the same quality. I changed the topic a little bit and discussing about the importance of velocity update. For a long history, the dead reckoning can help the GPS, dead reckoning can help the positioning where the GPS are difficult to use. But I would like to clarify that the velocity update, it helps a lot, but it is not the solution at the GNS denied environments. So in order to verify, first we derive the equation of position error after the velocity update. It described like this. And I input the before value, which is the same as I explained this drifting error, into the equation and compute how much the velocity update change before and after. And here is the result. And in order to compare the results, I take the fraction of each noise parameters. And this table shows the fraction, how much the velocity update shrinks the error of drifting error. And acceleration random walk becomes a half. Acceleration bias stability and gyro random walk becomes a quarter. And gyro bias becomes a 1/6. This one tells us the velocity update is useful and it clearly to shrink the error which is drifted. However, the value does not become the zero. It means every time the error will accumulate and finally it will exceed the integrity requirement, in this case, 0.1 meters. And I would like to tell that from this one, we need the position update, not the velocity update, is needed where the GNS denied environments. And in my knowledge, the LiDAR or the vision sensor is the only sensor which can provide the position update. In order to verify the idea so far, I did the simulation for the in order to verify the idea so far, we did the simulation. Here is a scenario of the simulations. I prepare a lot of scenarios, but we use the zero velocity update and wheel speed sensor. So that motion plan is one of the important factor because it decides the velocity of input. To get the motion plan, we used the bus traffic tracker in 2018 before the COVID. And here's the velocity as a commute time 5 p.m. Non-stop and stop scenario we prepared. The non-stop means the velocity does not stop anywhere. And stop means the velocity stop every bus station for 20 seconds. So first, I would like to show the result of stop and non-stop situations using INS and GNS. And the INS uses the STM300 tactical grade. Every scenario, I prepare the two results. One is a blue, the other one is a red. The blue shows a long track result. It means X or ahead directions. And cross track is the Y direction or side directions. Both figure has an X-axis shows a distance in meter. 0 is the starting point, 9 kilometer is the ending point. From 0 to 9, the building height becomes taller and taller. Y-axis shows 1 sigma error standard deviations. Because our integrity requirement is between 0.1 and 0.05, If the error exceeds 0.1 meters, the navigation system cannot provide safe navigation for self-driving car. If the error is between 0.1 and 0.05, partially it provides some of the case not. If the error is always less than 0.05, it means it provides a safe navigation always. So first we compare the stop and non-stop scenario using the same sensors. The non-stop scenario, clearly it is better than stop scenario, both cross and alongside directions. This is because the car goes through GNSS denied area quicker, and the navigation system can get GNSS signals before the INS exceeds error drift 0.1 meters. Now we integrate one additional sensor, which is zero velocity update. This non-stop is the same as this result. And the below one is a stop situation, but we add the zero velocity update sensors when it is the stopping. The result clearly, it is the same level of non-stop and stop with the zero velocity update, both along and cross track. The third one, we integrate wheel speed sensor, non-holomic and holomic constraint into the previous sensors. And at the long track, we can see some improvements, especially this and this, and continuity is extended. But I would like to show that especially because of non-holomic constraint effect, the cross-track continuity becomes almost twice of the without it. So the next evaluation is I use two types of INS. First is a tactical grade, and second is industry grade. As I showed the previous analysis, these two provide almost the same quality. As a result, the integrity evaluation shows almost the same. So far, we have already integrated INS zero velocity update, GNSS, wheel speed sensor, non-holomic and holomic. Even though we integrated all conventional sensors together, unfortunately, the error exceeds 0.1 meter after the 5 kilometers, which is a deep GNSS denied environment. So in order to modify it, we need some position reference. In our case, we use the rider. Also, the rider is important of the landmark density. So we prepare several landmark density for our simulations. The first is a traffic light pose every 300 meters, around approximately every 300 meters it appears. In order to make the condition same, we take only one landmark, closest to one landmark, when the landmark is the ranging in 60.5 meters. And traffic lights with a rider result shows some of the huge improvement happened, especially in GNSS denied environment. However, sometimes it exceeds 0.1 meter integrity requirements, so it tells us we need more dense landmark position reference. So now we change the landmark density from 35 meters to the 15 meters. The 35 meters, clearly the error goes down and it never exceeds 0.1 meters. If we change the landmark density to the 15 meters, the error does not 0.05 meters. So that we can tell that using the INS zero velocity update rider, GNSS, wheel speed sensor, non-holomic and holomic constraint, with a density of every 15-meter landmarks, we can guarantee the navigation system provides safe navigation for self-driving car in any time. This is an overview of our graph and the navigation. It shows the navigation performance. And it is clear that if we add one additional sensor, both travel distance describes the continuity and availability fraction, its availability goes up so that it is useful. However, if we evaluate the integrity requirement of the self-driving car, only the last sensor, it works for the integrity requirement. So here's the summary. Velocity update by dead reckoning can extend navigation continuity by bridging intermittent GNS signal availability. However, in a succession of GNS denied environments, position reference updates are necessary. In our case, LiDAR ranging from local landmark at every 15-meter interval to achieve 100% navigation availability. Intentional vehicle stops can extend navigation continuity by zero velocity update to the same level as a non-stop scenario. And finally, individual noise source examination shows that ion sensor cost deduction can be achievable without degrading the performance. Thank you for listening.
Thank you, Kana, for this great presentation. We will now accept questions from the audience. As a reminder, you can submit your questions using the Q&A button in your viewer. So it looks like we already have a few questions coming in, so we can go ahead and get started with the first one here. Kana, can navigation grade INS solve the problem?
Yeah. So this is a question I prepare to thinking the audience about the questions. So when you're sitting at the research, I'm wondering if we can use a navigation grade INS. We do not need any complicated sensor integration, or we do not need to use a LiDAR. But the answer is no. The navigation grade INS cannot solve the problem. The reason because as I evaluated the visibility of GNSS, the GNSS denied area is more than 4 kilometers. And here is my analysis of navigation grade drifting error, how much it reaches 0.1 meters. And it says that 71 seconds, the navigation grade of INS reaches 0.1 meter drifting error for 70 seconds. So that I divide this 4 kilometer denied area divided by 71 seconds, it's gonna be 56 meter per second. So the vehicle needs to go through this dense urban environment area 56 meter per second is the same as the train speed or 125 miles per hour. Yes, navigation grade INS can help it. However, in reality, it's not feasible at all. So that the navigation grade of INS is not the solution for this dense urban environment. I guess.
Okay.
The next question, please.
Yes. So next question. Automobiles are typically considered non-holonomic, physical systems. So what is the reasoning behind inclusion of holonomic constraints in the Kalman filter?
Yeah, so this one. The non-holonomic constraint, in my case, if the vehicle is typically do not move side direction, so that Vy equals 0 in my Kalman filter integration. Under the assumption of Vy equals 0 helps a lot. So that's the cross-track reaction. Always the V0 equals Vy equals 0 input into the Kalman filter, and it appears on the result.
Okay, we have another question here. Why was the tactical grade IMU not helping much when compared to the automotive grade IMU on slide 20?
Yeah. So this is, I'm so surprised, but it's back to my analysis of INS noise parameters. So typically, I agree with you. The automotive grade is less than the tactical grade. Tactical grade should provide better solutions, which I am thinking the first. However, if I consider the INS noise parameter step by step, the noise parameter consists of 4 parameters. And the gyro random walk and the accelerometer random walk is important. And the gyro bias stability is not important for self-driving car, only 50 minutes time drifting error. And back to the noise parameters of tactical grade and ELPS 2, the random walk value is not so much different. Especially the ELPS 2 provides us better random walk rather than the SDM 300. And angular random walk is the same in this case. So that this small, only 15 minutes evaluations, these two provide the same quality. And if you use another application or another time interval, then you're right, and the tactical grade might give us the good solution than the industry grade. But this is exceptional for the specific applications.
Okay, and have you considered errors contributed from GPS multipath, both from the buildings and from other vehicles moving close by?
Yeah, right. So in this, sorry. In this specific research, we do not consider the vehicle at all. I use the 3D map to detect the multipath, so that the answer is only the build. Yeah, I consider the error contribution to the GPS multipath is only buildings. However, I have already known, or I use the citation work using the track. And if the vehicle besides the track will cause a multipath as well, I would like to say we need to consider it because the dense environment has a big track, and especially in this scenario, there are lots of bus nearby the vehicle. However, we cannot predict how much or how often we see the bus, so that in this specific presentation, I only consider the building because it does not change every time.
Okay, great. Well, that looks like that was the final question from the audience. So thank you everyone for joining us for today's webinar, and thank you, Kana, for your time and preparation.
Thank you very much.
Thank you. We want to remind everyone that a recording of this webinar will be posted to our website, YouTube channel, and social media channels by this Friday, the 5th. Thanks again, and we look forward to having you join us for a future ION webinar. Thank you.